In this video, I'm going to explain the elastic collision in one dimension for the second case. So what is the second case? In second case, we are going to consider one mass is at rest. So you have to see the figure. In the figure, the first mass has the initial speed, but we have to consider the second mass is at rest. So we have to consider this V2 initial as 0. So if any object is at rest, its speed is considered to be 0. So what will happen after the collision? So after the collision, the first mass will move with the final speed and the second mass will move to the opposite of m1 and it will have the final speed of v2f. So here in this video, I am going to show you the derivation for getting the answer for the final speed of the first mass and the final speed of the second mass. Clear? So for this also, we have to consider the two main equation. The first one is the law of conservation of linear momentum and the second one is the law of conservation of kinetic energy. So what we studied in the theory, for both elastic collision and inelastic collision, the momentum is conserved, but the kinetic energy is not conserved for inelastic. But in elastic collision, both are conserved. Clear? But here, the main aim of this video, I am going to show the derivation for getting these two answers. What are the two answers? V1 final for M1 and V2 final for M2. That's it. Clear? Okay. First of all, I'm going to frame the equation of law of conservation of linear momentum. So I'm going to write the equation from the figure. So what we have in the figure, M1 move with velocity or move with speed v1I. So that means here I have to frame the equation according to law of conservation of angular momentum, sorry, linear momentum. Law of conservation of linear momentum. So I'm going to apply the rule for each mass. So we already know the formula for linear momentum P, which is equal to mass multiplied by the velocity. And we know the formula for the kinetic energy. The kinetic energy formula is half mv square. So I'm going to apply this rule for this case. So before collision, what will happen in the before collision? M1 V1 initial plus M2, our V2 initial is 0. So I have to put 0, which is equal to after collision. What happened in the after collision? M1 moves with the speed of V1 final plus M2 multiplied by V2 final. So this is the relation we frame from the figure. Likewise, I am going to frame the same equation for the law of conservation of kinetic energy. Clear? Okay. For law of, so better I can take this equation as the first equation. Okay. And for law of conservation of kinetic energy, as we already know, the formula for kinetic energy is half mv square. So I have to apply this rule for this case, half multiplied by m1 v1 initial square, and in the second object there is no speed, so it will come as 0, which is equal to, for the final case, half m1 v1 final square plus half m2 v2 final square. So I'm going to consider this is my second equation. Clear? Now what I'm going to do, I'm going to frame the first equation. So better I can write the first equation here one more time. By that it will be easy for getting the clear picture. Clear? So m1 v1I equal to m1 v1 final plus m2 v2 final. So here what I'm going to do, I'm going to move this term to the left hand side. So what will happen? These two terms will get the mass 1. Am I right? So by that I can take the mass 1 as a common. So if you move this term to this side, what will happen? M1 V1I minus M1 V1 final, which is equal to M2 V2 final. Clear? Okay. So in this equation, I'm going to take M1 as a common term. By that M1 multiplied by V1 initial minus V1 final, which is equal to M2 V2 final. Clear? So this equation I am going to take as number 1. Likewise, I have to write the same thing for the kinetic energy. If you see the kinetic energy, we can cancel this half both left hand side and the right hand side, right? So by that we will get M1 V1 initial square, which is equal to M1 V1 final square plus M2 V2 final square. Again, what I am going to do, as we took the same thing for the linear momentum conserved equations, I am going to move this term to the left hand side. I am going to move this term to the left hand side. By that, this term will take a negative value. So M1 V1 I square minus M1 V1 final square, which is equal to M2 V2 final square. And in this equation, I am going to take M1 as the common term. So M1, if you took outside, what will come inside the bracket? V1 I square minus V1 F square. Clear? Which is equal to M2 V2 final square. So I'm going to take, this is my second equation. Now what I'm going to do, I'm going to divide the second equation by first equation. So what I'm going to do, I'm going to divide the equation second by first. So what will happen? I'm going to divide this term with this term. I'm going to divide this term with this term. Clear? So let's work out. So M1 V1 initial square minus V1 final square, which is equal to M2 V2 final square. Now I have to divide this term with this term, which is our first equation, divided by M1 V1 initial minus V1 final, divided by here also M2 V2. Clear? Now I'm going to apply the a square minus b square formula. As we already know this formula, a square minus b square, which is equal to a plus b multiplied by a minus b. So I'm going to apply this rule. I'm going to apply this rule for this term. So by that, the above equation will become M1 V1 initial plus V1 final multiply with V1 initial minus V1 final divided by M1 V1 initial minus V1 final. In the right hand side, we have the same term M2 V2 F square over M2 V2 F. Clear? Now we can cancel some term. What are the terms we can cancel? I can cancel M1 with M1. I can cancel this V1I minus V1F with this term, right? Likewise, here also I can cancel M2 with M2, and one of this V2F I can cancel with this. So now we will have only a few terms. Am I right? So what are the terms we are having from here? We are going to get V1 initial plus V1 final, which is equal to V2F, right? So better I can take this equation as my third equation. Now what I'm going to do, I'm going to take the third equation, I'm going to substitute that equation here. Which equation? In the first equation. Clear? So better, if you need better, I can write the first equation here. By that it will be easy, right? So better I'm going to write the first equation here. So what is our first equation? Our first equation here is M1 V1 initial minus V1 final, which is equal to M2 V2 final. This is our first equation. Clear? Now what I'm going to do, I'm going to substitute equation 3 in equation 1. So that means I am going to substitute this V2F here, right? So by that, let me see what will happen. M1 V1 initial minus V1 final, which is equal to M2 multiply with, here we have V2F, am I right? In this place, I'm going to substitute this value. Our V2F is V1 initial plus V1 final, right? Now I'm going to multiply this M1 inside of the left hand side, and I'm going to multiply M2 in the right hand side of the bracket. So what will happen? M1 multiplied by V1I minus M1 multiply with V1 final. Clear? Likewise, in the right hand side, I'm going to multiply this M2 inside. So M2 multiply with V1 initial plus M2 multiply with V1 final. Clear? Understand? Okay. Now I'm going to make a small rearrangement of the equation. So what I'm going to do, I'm going to separate the term with V1 initial one side. I'm going to separate the term with V1 final one side. That means I'm going to move this term to the left hand side. Likewise, I'm going to move this term to the right hand side. Clear? So what will happen? M1 V1 initial, and when you move this term to the left hand side, it will take a negative value because previously it is positive. So if you move this to the left hand side, what will happen? It will take the negative value. So minus M2 V1 initial, which is equal to, and here I'm going to move V1 final. So M2 V1 final, when you move this term to the right hand side, what will happen? This negative becomes positive. So by the time this term will take positive value of M1 V1 final. Clear? Clear. So now what I'm going to do, I'm going to take V1 initial as a common term in the left hand side, and I'm going to take the V1 final in the right hand side. So what will happen? V1 initial, if I took as a common term, we will get M1 minus M2, which is equal to the right hand side. If you took V1 final as a common term, you will get inside the bracket as M2 plus M1, right? Clear? Okay. So here I'm going to take this equation. Which equation? The one which I showed with the star symbol. Right? So I'm going to frame this equation in terms of V1 final. So therefore V1 final, which is equal to this term, will come to the left hand side of the denominator, right? So by that, what will happen? V1 final equal to V1 initial multiply with M1 minus M2 divided with M2 plus M1, correct? So this is our equation for finding the final speed of the first mass. So better I can take this equation as a third biggest equation. Clear? Okay. So later on, or if you want to clarify, if you want to check our equation, because we already found the final speed of the first mass, better we can cross check our answer, because already I gave the answer here. So better I can copy this. I can copy this, and let's check what will be our answer, whether our answer is right or wrong. So here we have V1 final. Here also we have V1 final, V1 initial, perfect. In the numerator we have M1 minus M2, perfect. In the denominator, we have m1 plus m2. Both are exactly correct. Am I right? So that means our final speed of the first mass is perfectly right. So likewise, we have to find what is the final speed of the second mass. For that, I need this answer. So what I'm going to do, I'm going to substitute this third big equation in our third equation. What is our third equation? We have to go back. So this is our third equation, right? So if you can write this equation here, which is V2F equal to V1 initial plus V1 final. So I am going to write this equation here. By that, it will be easy for our substitution, right? So our third equation is V2F, which is equal to V1 initial plus V1 final. So now what I'm going to do, I'm going to substitute this equation in place of third equation. That means I'm going to take this V1 final and I'm going to substitute that value here. So by that, we will get the answer for the second final speed of the second mass. Clear? Okay, let's restart. V2F, which is equal to V1 initial plus, in place of this V1 final, I'm going to substitute this entire term. So what is our term? V1 initial multiply with m1 minus m2 divided with m2 plus m1, right? Okay. Now what I'm going to do, I'm going to take the LCM here. So what will happen to this term? If you need, I can just make a little bit enlarge this equation. Okay. So therefore, V2 final, which is equal to, I'm going to take m2 plus m1 as a common term, m2 plus m1 as a common term. So what will happen here? We don't have anything. So anything, because we have to take this value in the top. So therefore, v1I multiply with m2 plus m1, and this term we no need. We can write the numerator as it is, plus v1 initial multiply with m1 minus m2. Clear? Now I am going to multiply this v1 initial inside, and likewise I am going to multiply this v1 initial here also. Clear? Okay, let's see what will happen. If you multiply this v1 initial inside, your term will become m2 multiplied by v1 initial plus m1 multiplied by v1 initial, right? Clear? Likewise, here I am going to multiply this term inside plus m1 multiply with v1 initial minus, because plus into minus become minus, m2 multiply with v1 initial divided by m1 plus m2. Clear? In the left hand side we have v2 here. Clear? Now we can cancel some terms. You can see here we have m2 v1 initial as a positive term. Likewise here we have m2 v1 initial as a negative term. So I can cancel these two terms, right? So what is remaining? The remaining terms are v2 final, which is equal to m1 v1 initial plus m1 v1 initial divided by m1 plus m2. Now you can see m1 v1 initial, m1 v1 initial, which is equal to 2 times of m1 v1 initial, right, divided by m1 plus m2. So the left hand side is v2 final, right? So now better I can modify this equation. By that we can compare our final, actually this is our final answer, right? But anyhow I can modify the equation in the similar way what I show initial, am I right? So therefore v2 final, which is equal to, how I can modify it? I can modify it as v1 initial multiply with 2m1. When you multiply this, you will get the same term again, am I right? Divided by m1 plus m2. So now what I am going to do, I am going to check my answer. So as I already showed the equation, I'm going to copy that equation. I'm going to paste that equation near to my equation, which we derived now. Am I right? And then we can cross check our terms. So I'm going to copy this. I'm going to paste it here so that I can verify. Left hand side we have V2 final. Here also we had V2 final. Here we have V1 initial. Here also we have the same term. And here we have 2M1. Here also we have 2M1. In the denominator we have M1 plus M2. Exactly, our answer is right. Clear? So this is the proof for the elastic collision in one dimension if one mass is coming with some speed, if another mass is at rest. Clear? So please see the previous video, because actually we have two cases in elastic collision. The first case is for the moving masses. Two masses will have the speed. But in the second case, only one mass will have the speed, but another mass will have rest, because its speed is considered to be zero. Clear? So these are all the two cases we studied in the theory, especially in chapter number 9 from book Rules of Physics. Clear? That's it. Thank you.